So everything I've talked about so far in the lecture has been for a Gaussian response, and therefore we haven't had to introduce a link function because, of course, in a GLM, the link function for a linear model is the identity function. So what I want to do now is very briefly introduce how the mixed model idea extends to the GLM setting, the generalized linear model setting. So just as with the linear model, we can add random effects to a GLM to form what's known as a GLMM, a generalized linear mixed model. And a GLLM takes the form shown here. The expected value of y conditional on the random effects equals the inverse link applied to x beta plus zb. So the linear predictor now has a fixed effect part, x beta, and a random effect part, zb, and the link function g connects it to the mean exactly as we saw in the previous lecture. Conditional on the random effects b, the observations are assumed to consist of independent elements from an exponential family density with conditional mean mu and conditional variance phi times the variance function of mu. So all three components then of the GLM that we discussed in the last lecture are present. We have a distribution, the random component, we have a systematic component, and we have the link. But the model differs, of course, in that when we introduce the mixed element, it contains random effects components as well as fixed effects, and the model is specified conditional on the value of b. Okay, so assigning some distribution to the random effects, the formula for the likelihood involves integrating the conditional density of y given b against the density of b and integral over a q-dimensional random effects distribution. For the normal linear model, this integral has a closed form MLE solution. That's what we exploited in the previous section of the lecture, but typically a closed form solution is not available for non-Gaussian models, and so numerical maximization is required, and that can introduce complexity. So the key message here is GLLMs extend in two directions at once. They extend generalized linear models to dependent observations, and they extend LLMs to non-Gaussian responses. So a generalized linear mixed model then combines the distributional flexibility of a GLM with the ability of mixed models to account for clustered or repeated observations. And let me just give an example of a generalized linear mixed model. This is one that will be familiar to people in the transport field. It's called the mixed logic model, and it's used very extensively in transport. It extends binary logistic regression by allowing the regression coefficients to vary across individuals. And so for individual I, from the mixed logic model, we're able to derive the probability of choosing some alternative A, conditional on the random effects, is the logistic function of X transpose I beta plus Z transpose BI, where the BIs are normally distributed individual specific random effects. So this model combines all of the ingredients we've developed. We've got a Bernoulli response distribution, we've got the logic link function, we've got fixed effects, and we've got random effects. But crucially, what this model does, what it affords, is it allows the ability to capture unobserved heterogeneity between individuals by allowing their preferences or sensitivities to differ across the population. That's what the random effects are doing, and they're doing it in a way that wouldn't be possible with a simple GLM. And examples of the mixed logic model in transport include mode choice, route choice, vehicle ownership, stated preference experiments, and many other discrete choice models that some of you will have studied elsewhere in your degree.